Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having a look at quite a tricky question. It covers both year 12 and year 13 inorganic content, so we're looking at group 2 and group 7 reactions from the year 12 content, and then we're having a look at the reactions of metal ions in aqueous solution from the year 13 side. And they have done a number of tests on two aqueous solutions which they've labelled L and M, and we've been told that they both contain iron salts. And then from the series of tests that are done and the observations that we've been given, we have to identify what L and M are, identify every single precipitate that is formed within those different tests, explain why we get effervescence in the reaction of sodium carbonate with L but not with M, and give ionic equations for all reactions. So it is a really knitted together mix of year 12 content and year 13 content. So I'll try and highlight at each point which bit's which in case you're only in year 12 and you've only done the group 7 and group 2 chemistry up to date, or if you're in year 13 obviously you'll need to know all of this content. Ionic equations generally not very well liked, so again we can talk through those and kind of how we can work those out as well. So the first thing I'm going to do is just go through and identify what the results are telling us. So starting with L, we are adding ammonia solution slowly until it is in an excess, and that gives us a red-brown precipitate that when we add excess ammonia, nothing changes. When we add sodium carbonate to the solution to L, we get a red-brown precipitate, and we get effervescence there as well. We don't need to identify the effervescence, but we do need to explain why effervescence is seen there, but not in the box next door. Now, just because it says red-brown precipitate doesn't mean that it is the same red-brown precipitate. Now it actually is in this case, as you'll see, but certainly if we hop over to the observations with M, we have two different green precipitates that actually get formed here. One of the green precipitates forms when we add the ammonia solution. Again, nothing happens when we add the excess, but when we add ammonia we get a green precipitate. When we then add sodium carbonate, we get a different green precipitate. And again, year 13 students, you'd be expected to know what those two green precipitates are, and again, why those two green precipitates are different, why the red-brown ones are the same, and that links into the idea of the effervescence being seen with L but not with M. Okay, then the third row of our table, this is our year 12 component. So we're adding dilute nitric acid and then dividing it into two portions. We're putting barium chloride solution in one and then silver nitrate solution in the other. And we can see that with L, we get a white precipitate upon addition of the silver nitrate solution. And for M, we get a white precipitate upon addition of the barium chloride solution. So the first two rows are going to help us to identify the version, the oxidation state of the ion that we have here in L and here in M, and then the anions are going to be identifiable by these precipitates down here. Okay, so trying to think where's best to start. I wouldn't say that identifying L and M are the best place to start. I think it would make sense personally to identify the precipitates and then use those precipitates to help us to identify L and M, then go on to do the other 2 points here. So in the first row, the ammonia is acting as a base. Now initially these two solutions containing the iron, they will have been sort of hex aqua ions, and what will happen is the ammonia is going to act as a base, take off protons from the water ligands so that they become hydroxide ion ligands, and that will continue to happen until the overall charge on the complex is neutral, and then we'll get precipitation out of the solution. Now, we need to be aware that anything green is our iron 2+, and anything red-brown will be our iron 3+. So that's the first thing that we need to be aware of. So here, Fe 2+, and then on this side, oh, sorry, now I've done that wrong. On this side, Fe 3+, try again, and on this side, Fe 2+. Okay, then what we need to I guess be happy with is the idea of the ammonia acting as a base. So initially we would have, like say, Fe with 6 water ligands as our hex aqua ion. Adding the ammonia, we're going to get 3 protons being taken from 3 separate water ligands. So we end up with 3 water ligands, 3 hydroxide ion ligands, and that will bring the charge here down to neutral. So the red-brown precipitate is Fe H2O 3 OH 3. And there's no charge on that because the Fe is 3+ and each of these hydroxide ions is -1. What lots of students will do is they'll do a ligand substitution reaction and they'll try and swap the ammonia on. That only happens when we add the ammonia in excess, and that only happens with copper. So ammonia and sodium hydroxide, if we were to add that, they both act as a base in exactly the same way. They will both take protons, so the NH3 will become NH4+. That will happen 3 times, and we're going to have to write an equation for that, so you'll see that in a minute. That is the same red-brown precipitate that we get when we add the sodium carbonate as well. So because the Fe3+ ions are smaller with a greater charge, they weaken the OH bond in the water ligands more, which encourages the protons to leave more easily, and then those protons will react with the carbonate, and that will then give us water and CO2, which is the effervescence that we get here. We don't get that reaction with iron 2+ because the iron is not small enough or highly charged enough for that to happen. But the red-brown precipitate is the same in both of those rows. But the green precipitates are different. So the first green precipitate with the ammonia, that's going to be doing the exact same thing as we are with the Fe3+, but for the overall complex to become neutral, we only need 2 waters to lose a proton. So we have 2 OH minuses and 4 waters. So that would be like that. But with the sodium carbonate, as I said, the Fe2+ ion is not acidic enough for us to be able to get the same precipitate with the carbon dioxide gas given off. So what happens instead is the carbonate replaces the water ligand, so we just get iron carbonate. So because this is Fe2+ and carbonate is CO3 2-, that would be FeCO3. I should probably number these. So if I call that 1 and 1 and call that 1, then that's 2, 2, that's 3, that's 3. So that's what we've got with our iron precipitates. Then thinking about the year 12 content in the bottom row, if we add barium chloride solution to something and we get a white precipitate, the barium must be reacting with sulfate ions to give us a white precipitate. Barium sulfate is insoluble. So that tells us that the anion there is going to be sulfate ions. So that precipitate is barium sulfate. And for the white precipitate for the observations with L, we've added silver nitrate. Now for silver nitrate to be added and give us a white precipitate, when we see silver nitrate, should be thinking of halide ions. If it was chloride ions we had present, we'd get a white precipitate. Bromide ions would give us a cream precipitate, and iodide ions would give us a yellow precipitate. So the fact that it's white suggests that the silver from the silver nitrate has reacted with chloride ions, so then that will be silver chloride. And again, I need to number those just to make it clear. So 4 and 5, 4 and 5. So when it then comes to identifying L and M, we now know the cation in L is Fe3+, and we know the anion in L is Cl-. So L therefore is going to be, and it says identify, so we can write either the name, so long as we remember to put in the oxidation state of the ion. So iron 3 chloride or FeCl3, either will be accepted because it just says identify. And then M, we've got iron 2+, and then we've got the sulfate ions that give us the white precipitate number 4. So that's then going to be iron 2 sulfate, which again we can name, or we can give the formula FeSO4. Now, ionic equations are a pain, but there's a couple of ways of thinking about them, and certainly for the year 12 stuff, the way that I would think about it is we want to write an ionic equation that shows how we make this silver chloride, and we've got to think about what ions we're going to need to make silver chloride, and similarly what ions do we need to make barium sulfate. These are the observations that we or the formation of these compounds are the observations that we see, and an ionic equation is designed to show us how those things that we observe forming form. So I think it's easier to do those ones, and I guess it doesn't really matter what order we do them in, but I'll try and do them 1, 2, 3, I'm going to need to do one, or the formation of precipitate 1 twice, because they're going to be different equations even though it's the same precipitate. Sorry, that's why I paused. I'll figure that out in a minute. So for the silver chloride precipitate that we got with L, it's the silver ions from the silver nitrate, so Ag+, and they're going to be in a solution. It says silver nitrate solution. And it says that L is an aqueous solution, so therefore my chloride ions will also be in solution, and then that gives me my silver chloride white precipitate, so state symbol solid. That's what we observe. These are the ions that we need to then make silver chloride. Same idea for the barium sulfate. The barium chloride solution is providing the barium ions. M is providing the sulfate ions, so we've got Ba2+, again aqueous, plus the SO4 2- ions from our aqueous solution of M, and then that will give us our white precipitate of barium sulfate, BaSO4, solid. Okay. The top three are, well, certainly the formation of the red-brown precipitate and the first green precipitate. Those ones are quite tricky. The equation for reaction 3, or reaction to make green precipitate, which I've labelled number 3, is a little bit more straightforward. So this might sound confusing to people who haven't done the year 13 part of this yet, or even if you have, this might be slightly confusing because I've identified that M is iron sulfate, yet I'm about to say that the starting point of my equation here is going to be the hydrated iron, sorry, not the hydrated, the hex AQA iron kind of complex. And that's because we've got aqueous solutions, so when observation with M, when M dissolves in the water, we get kind of the sulfate part of M will be replaced by water in the first instance. And that's something that you'll get more familiar with the more of those types of questions you do. So we're going to start with Fe bracket 6 waters. So that's a hexa aqua complex, and we know that M is iron 2+ because of the green colouring, and then we're going to be adding carbonate ions, and we don't need to add the sodium. This is where the ionic equation bit comes in here. Sodium's not doing anything here, so we'll just add CO3 2-. That will then give us our green precipitate of FeCO3, and then we're going to get 6 waters. And we're essentially just getting a swapping of the ligands there, and then we're getting our normal formation of iron carbonate, ions 2+, carbonates 2-, gives us a compound of FeCO3. So that one's a bit more straightforward. For the one above, when we add the ammonia, and the ammonia is acting as a base, a little bit trickier. Again though, we are going to be starting with the same hexa aqua water complex. We're going to be adding ammonia. Now, I'll just write it as ammonia for now, but we are going to need to balance it. What I said would happen is each ammonia that we add will take a proton from one of the water ligands, and we want to do that until the overall charge goes down to 0. So for every proton I take from a water, that leaves an OH minus, and that's going to bring the charge down by 1 each time. So I need to do it twice. So that will then give me FeH2O 4 OH2. So I need there to be 2 ammonias, which will each take a proton. So that's going to give me 2 lots of NH4 plus as my second product there. So the ammonia is acting as a base, and a base is a proton acceptor. Okay. For these 2 reactions, even though the red-brown precipitate is the same, we are going to get different secondary products. So I'm going to have to write 2 equations for the formation of that red-brown precipitate, depending on whether I'm adding ammonia or carbonate ions. So I'm going to just split this into 2. We're going to be starting with the same thing in each case. So this time the hexa aqua 3+ complex, because we've got Fe3+ in L, which we know because of the red-brown colouring of the precipitates. In the first one, we're adding ammonia. And again, the ammonia is acting as a base. Now, for every proton that gets taken, the overall charge comes down by 1, so that needs to happen 3 times, which will then give me the FeH2O3 OH3 precipitate we identified earlier, and 3 NH4 pluses, because we need 3 ammonias to each take a proton from one of the waters. It's the same sort of idea with the carbonate, but A, the balancing of this is not very nice, and B, once the carbonates have assisted in the waters losing the protons, the H+ ions, rather than just going and joining with the NH3 as we've seen them make NH4+, the H+ and the carbonate actually react, and so that gives us water and carbon dioxide as other products. So we're going to get the same precipitate, but we're going to make water and CO2, because any acid reacting with a carbonate ion will make water and CO2. Now, balancing wise, it is that we need 2 of the initial hex aqua complex. We're going to make 2 lots of the precipitate, and then we need 3 carbonate ions, 3 waters, and 3 CO2. Now, one of the things that I'm a big advocate for is not rote learning those year 13 equations, is understanding what the ammonia is doing, what the carbonate's doing in each example, and if we had hydroxide ions, what they would be doing in each example, which is acting as a base. Then you can figure out how to put those equations together. Having said that, the balancing of that carbonate equation with our Fe3+ ions, I just remember the balancing, because otherwise you could be there for ages trying to figure out how to get those balancing numbers in there. So 2, 3, 2, 3, 3 is literally how I remember that. So for those, in terms of them being ionic equations, again, we are still looking at the formation of the precipitates. we can't just miss off other products that are made because our equations have to be balanced. And here we again haven't used the sodium of the sodium carbonate, we've just got the carbonate ions. These have all got charges, and then we've got our charges on our NH4 pluses as well. So bit different in terms of the year 12 ones compared to the year 13 ones, but they are all the equations that we need. Now the final thing I have to do, make sure I don't miss this out, is explain why effervescence is seen in the reaction of sodium carbonate with L but not with M. So I'll put that here. So the Fe3 plus ions are smaller and more highly charged therefore bond between O and H in the water is weaker, therefore the H plus ions, or the protons, are lost. To carry on down here, not ideal. Lost more easily. This would be one of those questions where you get at least a full page of lines to write on, which might have been a good sensible suggestion for me to do as well, but never mind. So if the bond between the O and the H in the water is weaker, it's easier for that bond to be broken, so the H plus ions are lost more easily, therefore the Fe3 plus is more acidic, and then we can say that the H plus ions react with the carbonate ions to produce CO2, which they can see from your ionic equation. So in terms of this year 13 reactions of metal ions in aqueous solution, there's 4 examples that we need to know. We've got the Fe2 plus and the Fe3 plus. The other 2 plus ion we need to know about is copper, and again we'd need to know the colours of those precipitates and any solutions that might be made when we add an excess. In that case with copper it's the excess of ammonia that then dissolves the precipitate and makes a solution. Again, be able to write equations for all of those as well. And then the other 3 plus example is aluminium, and that's a bit odd because aluminium isn't a transition metal, so all the precipitates will be white and all of the solutions will be colourless because it's only the transition metals that have the ability to form coloured ions. But the aluminium behaves in lots of the same ways as the Fe3 plus, so both 3 plus ions you'll get effervescence, both 2 plus ions you won't. You get a very different reaction with the sodium carbonate. Same idea with the ammonia, just differing numbers of protons that get taken. Same with the hydroxide ions, but with carbonate it ends up being very different. So there is a lot going on there. If you're year 12, focus on this bit and these 2 ionic equations down here. If you are in year 13, obviously you have to focus on all of it, but it might be that you haven't yet done the reactions of metal ions in aqueous solution topic, depending on when you're watching this video. But as always, any questions that you have, guys, please just let me know. I'm more than happy to answer them. And thank you so much for watching. Take care.